So, hello Stella, I hope you are doing well. Today we are going to do this exercise on, I think it's further math mechanics, whatsoever it still stays physics. So, in the exercise, it is said a particle P of unit mass, a particle P of unit mass. When they say unit mass, it means its mass is 1, falls from rest under gravity in a medium which exerts a resistive force of k square g v square newtons, where g equals to the speed of the particle and k is the constant. I think j is also a constant, which is the acceleration due to gravity. They say when t equals to capital T, v, the speed equals to 1 on k, and the particle has covered the distance x. Show that a 2gx equals to 1 on k square ln of the absolute value of 16 on the 15. B 2gt equals to 1 on k ln of the absolute value of 3 on 5. So this is a very simple exercise. As I always told you, you need to start an exercise by first doing what? You record the data, you do your sketch, and from there you start analyzing the question. Never start an exercise without doing a sketch, without collecting your data and doing your sketch first. So for you to easily see things, first start, you collect your data, and you do your sketch. So let's go directly. So they said, let me go back to the question. They said a particle P of mass, of unit mass, falls from rest. So let me record my data first. So as data, let me take this pen, data, as data, I have mass of P, let me call it MP, which is equals to 1, let's say 1 kilogram, because they said it's a unit mass. The particle is falling from rest, that is the initial velocity. The initial velocity must be equals to 0 meters per second. Okay, the initial velocity, let me write this, I'll write it completely. Let me write this. They said initial velocity u equals to 0 meters per second. The particle is also falling from rest. It also means that at time t equals to, if I will say 0 second, its displacement, initial displacement, if I call this x0, is equals to 0 meters. Okay, what do we have again as information? Let me go to the image. Okay, the particle falls from rest in a resistive falls from rest under gravity in a medium which exerts a resistive force. So the resistive force is equals to k square g v square newtons. Okay, let me go back. So the resistive force, so the resistive force, I'll call it Fr, has magnitude k square g v square newtons. And they say that v is the speed of the particle. V equals to the speed, and k equals to a constant. Okay. What next do we have? They said that at t equals to capital T, v equals to 1 on the 4k, and the particle has covered a distance of x. So this so at t equals to capital T, the velocity equals to 1 on 4k, and the distance covered, if I call this let's call this d0. If I call the distance over d will be equals to x. Okay, now what was the first question? The first question says this: show that 2gx equals to 1 on k square ln of the absolute value of 16 on the 15. The first thing we're going to do, we naturally draw our diagram first of all. So before starting the question, let's draw our diagram. So that's the data. So let's draw our diagram. They said the particle is falling under gravity from rest. So this is my particle. If I call this my particle, the particle is falling. Let's say this is the floor. The particle is falling. What are the forces? We are supposed to show the forces that act on the particle. So this is my particle. The particle is falling. So this is the direction of motion. The direction of motion. And I told you, whenever you know already your direction of motion, you have to do what? To orient your axis. And I told you, how do you orient your axis? You position that axis, you orient your axis, always orient your the positive axis in the positive direction. So this is where the particle starts the motion. Let me draw dotted lines like this. So from here, I'll draw my y-axis downward. So this is the j vector, my y-axis. This is my x-axis. This will be my I vector. Is that okay? So this will be my origin. You understand? So I have already oriented space. I've already oriented my axis. From there, this is my particle. The particle has what? It has a weight W, and there is a resistive force Fr which acts against its motion, because since it's a resistive force, it will act against the motion. So the resistive force will act in this direction. So I'll call this Fr. This is the resistive force. So we have already drawn our diagram. Now, having drawn the diagram, we can proceed to the questions. The first question says, A, show that 2gx equals to 1 on k square ln of the absolute value of 16 on 15. When you look at this, generally, the first thing you have to do when you look at this, it's like this x, we know that this x represents distance. You understand? So basically, in when you shall be doing when you shall be solving the question, you need to find a relation where you will have distance related to something. I don't know if you are trying to get what I'm saying. In this B question, you have time here. So you need to use an expression where you will have time related to something. Because this x is already directing you, that you need to have a relation where you have distance related to something. This time in this B equation is already telling you that you need to have a situation or an equation where you relate time to something. I don't know if you are trying to get what I'm saying. So let's go to the question. So let's do the A. Question A. We are to prove that 2gx is equals to what? Is equals to 1 on k square ln of 16 on 15. 1 on k square ln of the absolute value of 16 on 15. Okay, the first thing we have to do, I'll first apply, the particle is in motion. So the first natural thing that will come to us is to study the motion of the particle using Newton's second law of motion. You understand? So I'll just applying, let me take a red pen, applying Newton's second applying Newton's second law of motion to the motion of the particle, applying Newton's second law of motion to the motion of the particle, we have, so Newton's second law of motion states that what? The sum of the particle is undergoing if I would say translational motion. So there is no rotational motion. So the expression of Newton's second law of motion we are going to apply here is the translational form, which states that the sum of external forces, sum of all external forces must be equals to ma, which is the acceleration. Now, the question we have to ask ourselves, what are the external forces acting on the body? The only external forces are what? Are the weight and the resistive force. So we proceed. So we have the weight plus the, pardon, let me go back. The weight plus the resistive force Fr must be equals to Ma. Is that okay? Now we have to bring out the components, the different components of each of the forces. We are in which system are we? Which we are in an XY system. We are in an XY system. So the weight would naturally have a component in the X direction, Wx, Wy, plus, this is the component form. So plus Frx in the X direction, Fr in the Y direction must be equals to the mass of, this is MP, the mass of the particle, because it's the particle P. Recall that we related his mass to be equal to be called MP. So we're going to have, this is MP into, you have acceleration in the X direction and acceleration in the Y direction. Okay, now this implies, what is the X component of the weight? This is the weight. The weight is acting only vertically downward, so there is no component in the X direction. So this is 0. What is the X component? What is the Y component of the weight? This is our diagram. The weight is acting vertically downward. You understand? And it is in which direction of Y? In the positive direction of Y. So here we are going to have mg, mpg, yes, because it's the mass of the particle, plus the resistive force. The resistive force has no component in the X, so the component here will be 0. What is the component in the Y direction? It is acting, the resistive force has a component in the Y direction because it's acting vertically upward. And how is it? It is in the opposite direction to the positive Y axis. So we are going to have here minus, they say that its magnitude, so we are going to have minus k squared g v squared. Is that okay? Which will be equals to mp into, now the particle is moving in the Y direction. It's not moving in the X direction. So the acceleration in the X direction will be 0. Since the particle is moving only in the Y direction, the AY component will becomes A. Is that okay? So this is equals to 0 because there is no motion in the X direction. No motion in the X direction, and this becomes equals to A since the motion is in the Y direction. Okay, now this implies we are going to have the following systems. We have 0 equals to 0, and we have the system MPG, minus k square g v square equals to mp, yes, equals to mp times A. Is that okay? Okay, is that okay? So I will simplify this. They said that the particle has a unit mass, so mp must be equals to 1. So this equation becomes, I will have this is equation 1, equation 2. So this equation 2 becomes g into 1 minus k squared v squared being equals to what? Acceleration. Is that okay? This is equation 2. Okay. Now, the first question says we should prove that 2gx equals to 1 on k square ln of the absolute value of 16 on 15. Is that okay? I told you that there is x here. That simply means we have to look for in order to prove this, we need to have a relation where we relate x to something. Is that okay? We have to relate x to something. So in this our last expression, we know that acceleration is equals to dv on dt, but we cannot use this because our main aim is to prove something which relates x to what? To something. So the best thing to use will be what? We know that if we differentiate this implicitly, this becomes with respect to x, this becomes dv dx times what? Dx dt. Is that okay? So acceleration dx dt is the same as v. So acceleration is also equals to v dv on dx. Is that okay? We have already an expression. We have already something that contains what? Our x that we'll be looking for. So what I will do is that I will replace this acceleration by v dv on dx. So this implies I'm going to, let me go on the next page. Let me go on the next page. I'll divide this into 2. No, let me not divide this. So let me go on the next page. So on this page we had g being equals to g into 1 minus k square v square equals to a So we are going to have, so we have g into 1 minus k square v square equals to a. But we know that acceleration is equals to what? Acceleration is equals to v dv on dx. Is that okay? So from there, we're going to have g into 1 minus k square v square must be equals to what? Must be equals to v dv on the dx. Okay, remember something as I told you. The two variables here are what? Are v and x, because there is a dv here and there is a dx here. So let me bring terms in v to one side and terms in x to the other side. So this implies I'm going to have this. I'll bring dx like this and this whole term under this. So this will become g dx must be equals to what? V dv on what? V dv on the 1 minus k square v square. Is that okay? Okay. Is that okay? So so this implies now we have basically we have to find we have to remove this dx and this dv, and the as I told you in integration, to remove this we just introduce the integration sign. Okay, before introducing the integration signs, let me first introduce the initial conditions. The initial conditions, initial conditions, they say that at t equals to 0, at time t equals to 0, what was the distance? The distance d0 was equals to what? 0. What was the velocity? The particle is leaving from rest, so its velocity was equals to 0 meters per second. This is meters. And they said that at time t equals to capital T, what was the distance that the particle had covered? The particle had covered a distance x, and its velocity was equals to what? Its velocity was equals to, so this is the initial velocity. Its velocity was equals to, I think, 1 on 4k. Let me verify. Its velocity was equals to 1 on 4k exactly. Now we have already our boundary conditions. From there, we can proceed to the integration. So this implies g into the integral of dx, where how is x varying? X is varying from d0 to d. Is that okay? So the integral from d0 to d will be equals to what? The integral from what? V is varying from initial velocity to final velocity, u to v of what? This v dv all over what? 1 minus k square v square. Is that okay? Okay, let's substitute values. This implies g integral d0 is 0, d is what? X. Dx must be equals to what? The integral from the initial velocity is 0 and the final velocity. The final velocity is 1 on the 4k. Integral of v dv on the what? On 1 minus k square v square. Is that okay? Now, here we are simply going to have what? So we are going to have, this implies we are going to have g, the integral of dx is what? Is x. You understand? So we are going to have x boundaries from what? 0 to x, which will be equals to integral from 0 to 1 on 4k v dv on the 1 minus k square v square. Is that okay? Okay. Now, when we substitute the upper and lower bound here, we simply make x, this x minus this 0. So we are going to have what? This implies gx will be equals to the integral from 0 to 1 on 4k v dv on what? 1 minus k square v square. So we simply need to find this integral and substitute the boundaries. From there, we're going to have the answer. Is that okay? Now, we know that before finding, this is a definite integral. Before finding a definite integral, we have to do what? We have to find the primitive. So what I will do is that, what do you notice? Notice that this k square is a constant. K is a constant. So if k is a constant, naturally k square is a constant. What do you notice here? You notice that when you differentiate this bottom, we have already seen integrals of the form f prime of x on the f of x. I don't know if you remind yourself, f prime of x dx all over f of x is the same thing here. We notice that when we differentiate this bottom, if I do d of 1 minus k square v square, this will be equals to what? If I differentiate, v is the variable. Don't forget that v is the variable. When I differentiate this, I will have what? I'll have minus 2 k square v dv. Is that okay? I'll have minus 2k square v dv. So what are you having here? What you are having up here is simply what? You are simply having v and dv. So you notice that to have exactly what is here, to have exactly for this to be equals to what is on top here, we have to multiply top and bottom of this integral by what? We have to multiply it by minus 2k squared. Are you trying to see what I'm doing? So we notice that g of 1 minus k square v square is equals to what? Is equals to v is the variable. When I differentiate this is 0. When I differentiate this, I'll have minus 2k square v dv. Is that okay? Remember this formula, g of f of x must be equals to f prime of f of x dx. Dx because x is the variable. Dv here because our v is the variable. Is that okay? So when I notice already this, I'll rearrange this integral. This implies, and remember something, you can multiply an integral only by constants. I have the right to multiply by minus 2k squared because they said in the exercise that k was what? A constant. So naturally, k squared is a constant. We don't multiply integrals by variables. So this implies gx will be equals to what? I'll multiply top and bottom of this integral by minus 2k squared. Is that okay? So this will become, I'll have minus 2k squared all over minus 2k squared integral from 0 to 1 on 4k v dv all over what? 1 minus k square v square. Is that okay? So I'll bring this one inside. This will become gx will be equals to minus 1 on 2k square integral from 0 to 1 on 4k minus 2k square v dv all over what? 1 minus k square v square. So you notice already that, so this is what we're going to have. But recall that we saw that this was equals to this. So we're going to replace this by what? D of 1 minus k square v square. So this becomes equals to, this implies gx will be equals to minus 1 on 2k square. Integral from 0 to 1 on 4k. We replace this by d of what? 1 minus k square v square all over what? All over 1 minus k square v square. Is that okay? Is that okay? So what do we notice? We notice that we are already in an integral of the form d of big X all over what? A big X. What's the integral of this? We know that it is ln of the absolute value of big X. Is that okay? So this integral, so what this implies, gx will be equals to minus 1 on 2k square. I'll put boundaries. Ln of what? The absolute value of what? This 1 minus k square v square. Boundaries growth going from 0 to what? From 0 to 1 on the 4k. Is that okay? From 1, yes, 1 on the 4k. Exactly. So, so this implies our g of x, pardon, it's not g of x, it's gx. So this implies our gx will be equals to, I'll substitute the boundaries. So I'll start substituting the boundaries. So this will give me minus 1 on the 2k square into, I'll first substitute the upper bound. Yes, I'll first substitute the upper bound. Let me substitute the upper bound. I'll first substitute the upper bound. So I will have ln of what? The absolute value of 1 minus k square into 1 all over 4k, all that square. Is that okay? Minus what? The lower bound. I'll substitute 0. When I substitute 0 here, where there is velocity, I'll have ln of what? The absolute value of 1, which is simply 0. Is that okay? So this implies we're going to have gx being equals to what? Minus 1 on the 2k square into what? Ln, absolute value of 1 is 1. So ln of 1 is 0. So we're only left with this. So this will be equals to ln of what? The absolute value of 1 minus what? K square times 1 all over 16k square. Is that okay? 16k square. So this k square will go with this k square. So we shall be left with what? We shall be left with, we have gx being equals to minus 1 on the 2k square. Is that okay? On 2k square, minus 1 on 2k square into what? The ln of the absolute value of 1 minus 1 on the 16. Is that okay? 1 minus 1 on the 16. Yes. 1 minus 1 on the 16. Is that okay? Yes. So we have this. From here, we are going to do this. This 16 will multiply this. 16 times this is 16 minus 1. 16 minus 1 is 15. So this implies gx would be equals to minus 1 on 2k square ln of what? The absolute value of 15 on 16. Is that okay? Let's go back to the proof and see what we're supposed to prove. The proof says that, let me go back. The proof says that we're supposed to prove that 2gx is equals to 1 on k squared ln of the absolute value of 16 on 15. So we have already done half of it. From here, look at what I will do. This implies this 2, I'll bring it here. This becomes 2gx being equals to this minus 1. Recall that, look at something. Recall that ln of a to the, recall that ln of a to the n is equals to n ln of a. Is that okay? So I'll bring this minus 1 as a power. So this becomes 1 on k square. Is that okay? Ln of what? The absolute value of 15 on the 16 raised to the what? To the minus 1. Is that okay? But we know that, look at something. The absolute value of a on b is the same as the absolute value of a all over the absolute value of b. So this becomes, so this one becomes, it implies we have 2gx being equals to what? 1 all over k squared ln of what? We're going to have, let me put brackets here. I'll have absolute value of 15 all over absolute value of 16. All that raised to the minus 1. But we know that a raised to the what? A raised to the minus 1 is the same as 1 all over a. So here we are going to have 1 all over the absolute value of 15 all over the absolute value of 16. This will be equal to the absolute value of 16 all over the absolute value of 15. Is that okay? So this implies 2gx will be equals to 1 all over k squared ln of the absolute value. Wait, let me write this. Ln of the absolute value. Ln of the absolute value of 16 all over what? The absolute value of 15. And from there, when we use this property, this becomes equals to, this implies 2gx will be equals to 1 all over k squared ln of the absolute value of 1. 16 all over 15. So that's what you were asked to prove. Is that okay? So it's very simple. What do you notice here? We notice that we simply applied some rules of integration. I told you when we did integration, I showed you how do you integrate f prime of x dx on f of x. I told you how to integrate this. You recognize this top as d of f of x all over what? F of x. So this becomes ln of the absolute value of f of x, plus our constant k. So this is what we notice here. So it was a very simple exercise. So in the next video, I'm going to do question, the B part. You understand? So in this question, the main thing you had to notice for you to know how you had to move was, this was distance. The question you have to, what you have to understand is that you have to bring out an expression of acceleration that relates distance to something, whatever the thing. And the only thing we know that acceleration is v dv on dx. You understand? So that's the end of this A part. Let's move to the B part. See you in the next video.